A very good welcome to another session on mobile communication networks. So I have joined the session. So wait for another 2 or 3 minutes, then I'll start today's presentation.
Okay, sir.
Okay, I will start unit the wireless channels. So in last class we had seen of the signal propagation mechanisms, reflection, refraction and scattering. We had seen the reasons. What are the problems in designing a wireless? It's a unit to wireless communication, the code channel, the shadowing, line of sight, followed by the three different mechanisms: reflection, diffraction, and scattering. The multipath fading introduction. So where multipath fading is being used, where large scale propagation is used, we had seen as and we had seen an example of the large scale fading effects with the line of sight and non line of sight examples towards them. Then we had started with the phase propagation model. Then Friss transmission equation. Yeah, in the example of the far field distance calculation given operating frequencies. And we have done two assessment one and given the values and answers. Similarly, we have two the same relevant example. Calculated this, and we had came to a conclusion that the choice hertz of not using a lower frequency. We'll solve another example. It is power. The transmitter produces 50 watts of power. Express the transmitted power in units of meter and decibel watts. So how to present? Okay, and the second question is, if 50 watts is applied to a unity gain 900 megahertz frequency, power in decibel meter is distance of 100 meter from the antenna. And then the question is extended that what is the received power at assuming unity gain for the received. This is the example. So solution for this given here. We'll transfer 50 watts of power. T is equal to 50 watts. We need to express it will express in decimal meter is that 10 to the base 10 divided by 1 milliwatt. We calculate this, we'll be getting in terms of decimal meter. D. Base 10 PT, which is 50 watts, you substitute 50 watts, you will be getting 47 decibel meter. Thank you. Okay. So next, in terms of decibel watts, how to calculate decibel watt is 10 to the base 10 PT divided by watt, so which is 10 log to the base 50. So 10 log to the base of 50, which is a transmitted power, we get 17 decibel watts. Kindly check it out. Check it out. You're getting 17 decibel watts. Is that clear with the option A? Sorry, question number A. Exact any queries in 2A? If you're able to 2A,
Hello, sir.
Yes, please. What are your queries?
Sir, no, today your voice is being cut, sir. It's not clear, sir. Maybe network issue, sir.
Is it audible now?
Yes, sir.
Any queries in 2A? If not, I'll proceed on to 2B. So the question we need.
Sir, again there is some
So if
disturbance.
50 watts is applied to unit antenna with 900 megahertz carrier frequency, find the received power in decibel meter. Find the power in decibel meter at a free distance of 100 meter from the antenna. So the distance is 100 meter from the antenna. Okay, so let us find. So we need to calculate the received power. The formula is PR of D. PR of D is GR lambda squared by 4 pi square D square L. So this is the formula. Received power is equal to PT GT GR lambda squared by 4 pi square D square L. First, let us see what is this PT value. is is 50 watts. Okay, for 50 watt, we need to find the power in decibel meter. So already in subdivision A, we had found it as 47 decibel. 44. So T by PT. Then GT transmitting gain, GR is a receiving gain. So in the antenna, we have gain as given in the question. Unit gain antenna. So equal to 1. So distance is D is equal to 100 meter, and L is taken as 1. Okay. So substitute that in this formula. PT 47 decibel, GT GR1, lambda value equal to P by F. So already we had found in example 1, lambda is equal to C by F for 900 megahertz, 0.333. So make a note of that and substitute divided by 4 pi square d square into F. Okay. Multiplication 3.5 7 into 10 power minus 6 watts. 3.5 approximately 3.5 into 10 power minus 3. So take 10 logs. Now to measure in terms of decibel, quite find this decibel. So decibel the formula is 10 log to the base 10 p divided by 1 milli. Okay, so 10 log to the base 10, 3.5 into 10 power minus milliwatts divided by 1 milliwatts. So 1 milliwatt 1 become 1. So remaining is 10 log to the base 10, 3 minus 3. So using your calculator for 100 meter as, you'll be getting it as minus 24.5 decibel meter. So next line for 10 kilometers. What is the received power for 10 kilometer? With the same specifications, find it for 10 kilometers. So PR of 10 kilometer, which is 10 into power 3, which is 10 into 1000. Okay. Here it is this for 1000 meter, like this. So 3.5 to 10 power minus 3 divided by 10 power 4. You will be getting 3.5 to 10 power minus 7 milliwatts. This is the solution for 2B. So any queries in 2B? Any queries in 2B?
Okay.
Any queries in 2B? And type in chat. Okay, so this is how to calculate transmitted power in a decibel meter. What this is important, and how to calculate the received power, which is operating with some frequency, and some watt of power is given with a gain. This is the procedure. So any queries you can type, or I'll proceed on to next. So these are the numerical examples. No queries. Okay. Thank you, Vaibhav, for your feedback. So next is the sight. So in previous class, I had shown you line of the line of sight. From the transmitting antenna, the user or the receiver will obtain the signals, any obstacles, or without any reflection, refraction, or scattering. So in non-line of sight, the electromagnetic wave or the radio will be reaching from the transmitting antenna to the different obstacles or stages. This one, this 2 is your reflection, this 4 is your diffraction, scattering due to this. So all this comes under non-line of sight. So this non-line of sight is an best example of your multipath propagation. So another example also here, a car is there. Okay, the car will receive the signals due to reflection. You can see car is denoted by reflections or reflection. So due to diffraction signals, and due to scattering it may receive. Okay, so this we call it as multipath propagation. So the receiver through different paths. Okay, your car, it receives signals from a transmitter, different paths. So the paths could arrive with different gains. If there is different path, obviously different phase and different delays. So even a small distance variation will have a large amplitude variations. So this is the physical phenomena behind multipath propagation. So R is your reflection, D is your diffraction, and S is your scattering, as shown in this example. Small scale reading. So the factors that influence in multipath propagation. This results in multiple version of transmitted signal, multiple paths, multiple versions, multiple phases, multiple delays. Next is speed of the mobile. Speed of mobile is much more, then it results in random frequency modulation, Doppler shifts. Next is the surrounding objects move at a greater rate than the okay. The surrounding objects with respect to the receiver move at a greater rate than small scale multipath. And next factor that influences at the transmission bandwidth of the signal. If the transmission bandwidth is greater than the bandwidth of the multipath channel, then small scale fading may occur. The bandwidth of the signal plays a major role in small scale fading. The transmitted signal will have a bandwidth which is greater than the bandwidth of the channel. We have three parts in the communication, and in between transmitter and receiver we have the channel. So this will be very much lesser as compared to the transmitter's bandwidth. So fading may occur. So due to this above factors, small scale fading effects, which are rapid changes in the signal strength over a small travel distance. Even though the signal travels distance or a shorter distance, the power which is being transmitted will vary. Means that there will be more fluctuation of the transmitted signal. It is being over the channel. Then random frequency modulation due to varying Doppler shifts, different multipath signals. Due to multipath signals, frequency will modulate at a higher rate. So then caused by multipath propagation delays. The physical phenomena of multipath. The physical phenomena for the multipath is what we are seeing: diffraction, scattering. So reflection is when signal encounters a surface that is large relative to diffraction occurs at the impenetrable body that is to the length of a radio wave. The waves bending around the sharp edges of the objects, as I had shown you in the diagram. Scattering occurs when an incoming signal hits an object whose size in of the signal or less than that. About the reflection. So reflection occurs when the radio is incident upon a boundary between two materials, the air and the ground, with different electrical characteristics. Examples: reflection. So reflection from foliage is also an example. Foliage is the densely available leaves, or denser leaves, which can cause reflection also. So this reflection interfere with the original signal either constructively or destructively. So a ray attenuates by factors that frequency, the angle of incidence, and the nature. With respect to its thickness. The amount of reflection will always depend upon the reflecting material which is being used or which is being present. So smooth surfaces of good electrical conductivity are efficient reflectors of radio waves. The Earth itself would be a fairly good reflector. So there is a reflection model that we're using, which is GRM, two-ray ground reflection model. Receiving antennas will have a direct path as well as a signal ground. The receiver will receive the signals not either along with the line of sight error. Okay, I'll show you that model as in this diagram. So here is a transmitter with a height HT, and here we have a receiver which is present at a height HR from the ground. Okay. So when a communication the transmitter emit signals. So during emission, one signal will directly the receiver, which is EL field outside, and with so this is your incident angle. Theta. The transmitted signals are falling on the ground and it is reflected towards the theta naught. So this is your reflected wave ER, which is equal to EG. We can write the electric field reflected wave, which is since ground is reflecting, so we call it as electric. So then the total electric field which is received will be to the direct line of sight component and the ground reflected wave, which is ER. In all transmitter and receiver that is to be considered. Ground reflection model. So in a single direct path between the base station and the mobile is rarely the only physical path for propagation. Hence, the free space propagation model in most is used alone. So hence, we use today GRM. Both the direct path and ground reflected propagation path between receiver. So this was found reasonably accurate for predicting large-scale signal strength over several kilometers radio systems using tall towers. The tall tower will be placed at 50 meters. For that, this ground reflection model works in a better way. Okay. And the maximum distance of D can be up to 10 kilometers. So for that, and this was very much helpful in designing a microcell concepts in urban. So this is how do we we have a transmitter, receiver, which has been separated by distance D. The height of the transmitter is taken as HT. HR. So you can find this point. If HR is the distance, which is always less than HT, you find the point AB. Pythagoras theorem. Okay. Now, a drawing line equivalent to this. So this will become HR. This is kind of side D. This is a model. So angle BC. In the diagram, I'll show you. This point, the transmitting antenna receiver height is now this point is 10 angle. Using the hypothesis theorem, dd square, which is this one, and we can find ht minus hr the whole square plus d square. Okay. Minus hr the whole square divided by. So as the square root of ht minus hr the whole square plus I think you're able to see now.
Yes, sir.
Yeah, yeah. If it gets broken up, I'm not sure why is it like that. Using an Airtel mobile only. Okay, no problem, no issues. So by using uh, hypotenuse theorem, we can for this triangle ABC, this triangle find the distance D. So DD will become D square 1 plus HT minus HR the whole D square the whole square root. So this DD represents your binomial series. So it can be written as D is taking a common by 2 HT minus HR divided by D the whole square. So same step for triangle BCD. You can see BCD, B, which is an exact replication at a okay. So B C D. Dr is equal to D 1 plus half of HR divided by 2 the whole square. Why? Because hence it is being reflected. Okay, from here reflection occurs. So HT plus HR. This is HT minus HR. So for BCD we'll be getting like this. So next is the path difference between the reflected and the direct wave. So reflected wave is represented and the direct wave is represented as ED. So the phase difference will be different into wave number. With that we can easily find the value of phi. ED which is 2HTHR divided by D. Of the transmitting antenna, HR is the height of the receiving antenna, D is the distance between and transmitter. So phi will be is equal to Dr minus into beta. So 2HTHR divided by D into beta in beta 2 pi by lambda. So substitute and simplify, we get the phase phi as 4 pi HTHR divided by D lambda. So this is your phase difference. So next, how do I calculate the power for this two-ray model? So received power can be calculated as the received power, which is equal to 4 PD 4 pi HT HR divided by 2 lambda into D. So PD is your in free space. So the power received for an reflected plane will be PR is equal to 4 PT GT GR into lambda by 4 pi D square the whole square sine 2 pi HT HR divided by lambda D. So here the angle theta will be very much smaller. So sine theta will be equal to theta HT HR is very much less than D. Theta will become small. So the distance between the transmitting and receiving antenna will be very much higher as compared to the receiving antenna. So theta will become small. So we can equate the equation as PR is equal to PT GT GR HT HR divided by D square the whole square. Formula for Fourier reflection model. Find the free space propagation model received power calculation PR. I'll show you that again. This is your first transmission equation for far field pre-propagation model. PR of D is equal to PT GT G 4 pi square D square L. So similarly for two-ray model, two-ray. We received PTGTGR into HT HR divided by DC the whole square. So now let us see example number 3. Let us see example number 3 such that you can understand this reflection model, solving it in a better way. A GSM network operates 900 megahertz GSM 900 cellular radio system with the 20 watts transmitted power. If it is 20 watts transmitted power, keep in mind it is PT, okay, in watts, which is being transmitted from base station transceiver, so which is BTS. Then the gain of and mobile station is 8 dB and 2 dB respectively. Meaning is that station will have a gain GT as 8 decibel, and the mobile station which we are using is, so make a note of that. So GT, yeah, 2 decibels. So write it. Then station receiver is located 10 kilometers away. So the distance between the base station and the mobile is 10 kilometers. So D is equal to 10 kilometers. Make a note of that. Then antenna for base station antenna height is 200 meter. So HT is equal to 200. So which is HR is 3 meter. So right, HR is equal to 3 meter. So by assuming plane earth loss, so the term you need to identify. So assuming plane earth loss, which is your two-ray model or ground reflection model. So by assuming a plane earth loss between a base trans receiver station, we need to calculate the received power at mobile. So the received power at mobile station is always the power which is being received. So list out the parameters which is given. So frequency given, distance 10 kilometer, the transmitted watts, measured in watts. So convert everything into dBm. So 10 log to the base 10 or 20 divided by 1 milliwatt. So on simplifying, we'll be getting 43 decibel meter. So as we are done in 2A, similarly find gain of the transmitting antenna, which is 8 dB, convert it to PM, which will be equal to 6.31. So 10 log of 10 log to the base 10, 8 dB. We get 6.31. Similarly, GR given is 2 dB, so convert 1.58. So keep all these things. Then, which is the height of the transmitting antenna at this transceiver 200 meter and receiver, which is mobile station, is 3 meter. So HT 200 meter, HR is 3 meter. So then we need to find the received signal at the mobile station. PR is equal to PT, GT, GR, HT, HR, D, square the whole square. So this is the so substitute all these things, we get 7.18 nanowatts. So in terms of decibel, in terms of formula. So any queries in this example number 3? Any queries, type in chat box. Okay, I'll give you 3 or 4 minutes of time. Kindly see that. And any queries, type in chat box. Okay, since I any queries in chat box, so I'll proceed on to the next slide, which is scattering. So this scattering occurs when the radio signal, as shown in figure, a radio signal or a radio path sender is a transmitter TX, receiver RX, obstructed by an impenetrable body, means that the signal cannot surface of that body, and by a surface with irregularities or sharp edges. Okay, so is where an scattering occurs. So scattering occurs when the radio path between transmitter and receiver is obstructed by an impenetrable body and by a surface with sharp irregularities or edges, sharp edges. We call it as scattering. The received field strength decreases rapidly as deeper into obstructed region or the shadow region. The diffraction still exists and often has sufficient strength to produce a useful signal. The diffraction explains how radio signals can travel urban and rural environments without a line of sight path. So the phenomenon of diffraction can be explained by the Huygens principle. All points on a wavefront can be considered as a point sources for production of secondary or secondary waves that combine to produce a new wavefront in the direction of you had studied in your physics, which are also familiar in reflections issue. So the field strength of the diffracted wave in the shadow region is of the electric field components of all secondary wavelets in the secondary space obstacle, so which is represented as OBS. So the medium in which the wave travels may consist of objects with dimensions, the length, and where the number of obstacles per unit volume would be, such as the rough surfaces, small objects, foliage, street lights, lamp posts, etc. There are many more. Okay. So the general difficult model, it is very difficult to model because the conditions. So modeling position of every street sign is not feasible. Every small objects, every rough surfaces on the streets is not possible. So action will exist. So here is an example of a scattering. If a wave falls on foliage, this it will in this manner. So this is an example of scattering. This is an example of reflection. And this is an example of diffraction. And after undergoing all this process, so the large-scale path loss model is determined for free space, urban areas, cellular shadowed urban area, built-in line of sight, obstructed buildings, obstructed. So there is a design being made, or which is being considered. Space, the path loss should be 2, or n value should be 2, and in an urban it should be around 2.7 to 3.5. For a shared radio, it should be 3 to 5. In a building, right region should be around 1.6 to 1.8. In an obstruct, the design of the path class exponent should be from 4 to 6. Fact is, it should be around 2 to 3. So now we are going to find the propagation range with respect to the environment. At phones, the propagation range should be at 3. In factories, 1.6. In storages, large storages, it should be 2.2 designing factor. In offices with multiple floors, 2 to 6 propagation range. In offices with same floor, 1.5. In urban microcells, 2.7 to 3.5. And urban macrocells, 3.7 to 6.5 is the range. Any queries till now? If there are any queries, you can type in chat box. Okay, no queries. Thank you. I'll proceed on to the next topic, which is Doppler shift. So the Doppler shift or the Doppler effect occurs when the transmitter has relative velocity. The Doppler effect occurs when the transmitter and receiver will have relative velocities. So here is an represented in red is always object receding long red waves, and blue indicates object approaching short blue waves. So this I'll show you Doppler effect. So here is a source which is in vehicle which is at, and we have an observer who is watching this at rest. So resting sound source. So now let us see. The source emits an electromagnetic. It goes, it goes, it goes, it goes, goes. It emits at a particular frequency. So the source is represented as Fs, and at observer it is represented as F0. And the frequency, the vehicle is of 340 meter per second. So now let us see. We are assuming that Fs is equal to the observed frequency is equal to the source frequency. Okay. So resting sound source. So in the next, I'm going to show you source moving towards an observer. So the source, which was at rest in the previous case, is now going to move towards the observer. Now let us see. It is moving. Okay. The source is moving. It is generating a frequency Fs, observing at a frequency F0. So here F0 is greater than Fs. So observer hears increase of the shorter wavelength as the source nearer to the observer. Okay, if f naught is greater than fs. So next, the vehicle is passing or it is moving away from the observer. Now let us see. The sound source is moving the observer. So the sound source will have fs. The observer will have a frequency f naught less than fs. So observer hears decreased pitch or long. So with this, you can able to calculate the Doppler shift. So this is called as Doppler effect. So how do I calculate this Doppler? Del L is very much smaller. V is vehicle or the mobile. Lambda is the, and if the frequency shift is positive or negative, means that if it is positive, it is moving towards. It is negative and it is moving away. So the phase difference can be calculated by del phi is equal to 2 pi del lambda del L by lambda, which is 2 pi d cos theta by lambda, and the Doppler shift either positive or negative. Positive means moving observer, negative means moving away from the observer. Calculated by fd is equal to 1 by 2 pi del phi divided by del t, which is cos theta. So this is an example. Doppler effect is that when a wave source each other, the frequency of the received signal will not as the source. When they're moving towards each other, the frequency of the received signal is higher than the source. When they are opposing each other, the frequency decreases, which is FT. Doppler shift in frequency can be given as equal to FC minus FD. FD can be calculated by V by lambda cos theta. Example, consider a transmitter which radiates carrier frequency of 1850 megahertz around 96 kilometer per hour. The speed of the wave 96 kilometer. So V is equal to 96 kilometer per hour. Convert that meter per second. Okay, meter per second you convert velocity, because the velocity measurement is meters. Then we need to compute the receiver carrier frequency if mobile is towards the transmitter and directly away from the transmitter. Okay, towards the transmitter in the sense it is moving towards the, directly away from the transmitter means it is moving. Then we need to find in a direction perpendicular of arrival of the transmitted signal. Okay. That means there is no Doppler shift in that. So this solution can be obtained by the formula which we had seen just now. This one. B is equal to V by lambda cos theta. So FC is given 1850. So FD can be calculated from this V divided by lambda cos theta. Okay. For A and B, assume cos theta is 1. Then we'll get some value. So that plus is your carrier frequency, which is transmitter. And FC minus FD is the frequency which is moving away from the transmitter. So now here you may need to find no Doppler shift. So if there is no Doppler shift, means theta is 90 degree. direction arrival, which is in a direction perpendicular to the direction of arrival means it is theta is 90 degree. So cos 90 is 0. So no Doppler shift. So this is the Fs is equal to, so we get no Doppler. So any queries in example 4? These are fundamental of your mobile communication. Any queries, type in chat box. Queries in example 4. No queries. Thank you. Okay, then you can fill Google form. It is given in chat box. And hoping you to see in another session. Any queries? Another 10 minutes. I'll be available. You can raise your queries.